We will now talk about the significance of the orbital quantum number L and what it tells us about the electrons. The magnitude of an electron that has an orbital angular momentum quantum number L is given as square root of L plus 1 h bar. So the magnitude of the orbital angular momentum, we can show this with absolute value L vector of an individual electron is given as L magnitude is square root of L plus 1 h bar. Okay, so the values that L can take are 0, 1, 2, 3, all the way up to n minus 1, a principal quantum number minus 1. Each L value has a name, S for sharp, P for principal, D for diffuse, F for fundamental. These are just spectroscopic names because of the way they look on the spectrum. So for L equals to 0, notice that the magnitude of the orbital angular momentum is 0. So what does that tell us in terms of the magnetism? So electrons in the s orbital do not contribute to the magnetic dipole moment of an atom from due to their orbital angular momentum. So we have no contribution from the orbital angular momentum of electrons in the s orbital. S electrons, if you remember the spherical harmonics for s electrons, it has the spherical shape. They have a finite probability of being at the nucleus so L is equal to 0. P electrons, on the other hand, have a 0 probability of being at the nucleus. For L equals 1, they must have an angular momentum, so they cannot be at the nucleus. N equals, well, you can see that also in the shape of the orbitals that it goes to 0 at the nucleus, so you don't have electrons, a finite probability of electrons being at the nucleus. Actually, the same thing is true for D and F as well. Only for S electrons we have a finite probability of being at the nucleus. So N equals to 1 gives us L equals to 0 as the only possible value of L, so that is our s orbital. N equals to 2 gives us L equals 0 and 1, so s and p orbitals possible. N equals 3 gives us L equals 0, 1 or 2, which means s, p, and d orbitals possible, etc. So that's how we see the hierarchy of orbitals. Now I want to say a few words about the energy of these orbitals. So we're going to have a remark here. So we talked about the principal quantum number n, and we said that they determine the energy of the electrons. So if you look at sp and d orbitals that have the same n value, the principal quantum number value is the same, have the same energy, this is strictly speaking correct for hydrogen. But if we have atoms with more than one electron, so that means any other element in the periodic table, we will have also a contribution from electron-electron interactions effect. So these interactions will affect the relative energies of states. So that this statement about the principal quantum number and giving us the same energy is no longer true. We have a change in the energy due to the presence of other electrons. So we have electron-electron interactions that will affect the energy values for these electrons residing in these orbitals as well. Okay, so in summary, we talked about the significance of the orbital angular momentum quantum number L. It gives us the magnitude of the orbital angular momentum, square root L plus 1 h bar. L can take values between 0 and n minus 1, and each one, L equals 0, is named S orbital, L equals 1 is named p orbital, L equals 2 d orbital, L equals 3 f orbital. So these are spectroscopic names: sharp, principal, diffuse, and fundamental. And notice that L equals to 0 implies 0 angular momentum magnitude. So electrons in the s orbital can reside, they have a finite probability of being at the nucleus. However, this is not true for any other orbitals, p, d, f. It's not true. And the way we name these, so for n equals 1, we decide that there is only one value of L, 0, that's s orbital. For n equals 2, L can be 0 and 1. These will be s and p orbitals, so on and so forth. And finally, we have a remark about the energy of these electrons. If you have a one electron system, the hydrogen atom, then the principal quantum number n does determine the exact energies of these electrons. But in atoms where we have more than one electron, electron-electron interactions will affect the relative energies of the states, so that this is, strictly speaking, this is not true.